Okay, so we now come back to analysis, and we are going to look at the fifth section of chapter 3. If you remember, we were going through set theory, so it's now time to look at Cartesian products of sets. So far we have seen three operations on sets. One is union of two sets, the other is intersection of two sets, and the third of course is the difference of two sets. Apart from these, there is Cartesian product also. It's also just like that, an operation. So let us see what this is all about. Although you probably already know all these things, but now we are going to look at Cartesian products of sets from Zermelo-Fraenkel choice set theory point of view. So the first definition is this. Ordered pair. Given any objects x and y, possibly equal, they may be equal also, they may be the same thing. We define the ordered pair x comma y to be a new object whose first component is x and whose second component is y. So if we are given two objects x and y which may or may not be equal, then we define an ordered pair to be a new type of object which looks like this, which has x as its first component and y as its second component. We sometimes also say that x is the first coordinate of this ordered pair and y is the second coordinate. That also sometimes we say. Two ordered pairs x comma y and x prime comma y prime are defined to be equal if and only if their corresponding components are equal. That is, x comma y is equal to x prime comma y prime if and only if x is equal to x prime and y is equal to y prime, which is natural also, because then they will be the same thing. Okay, now this means, this definition of equality means So for instance, the ordered pair 3, 5 equals the ordered pair 1 plus 2, 3 plus 2, but is distinct from the ordered pairs 5, 3, 3, 3 and say 5, 5. So in this respect, ordered pairs are not like sets. In ordered pairs, this word ordered means that the components, the order in which the components are appearing, that matters. 3, 5 is not equal to 5, 3. So in this respect, sets are different from ordered pairs. This is in contrast to sets, where the sets consisting of 3 and 5, if you write it like this or like this, you write 5 first followed by 3, they are actually equal. Okay, so that is basically the idea of an ordered pair. It's after all a set, it's a collection of some components, but order matters. Now there is a remark about this definition. Note that the above definition is in part an axiom. The above definition is in part an axiom. It's not that we are using only the axioms of set theory that we have got so far to define this. Look at this. We define the ordered pair to be a new object. It is somewhat like defining a function. If you remember, here in this treatment of functions that comes under set theory, we define functions to be a new type of object. So something like similar has happened here. We have defined ordered pairs. Given two objects x and y, we have defined their ordered pairs to be a new type of object that we are introducing in our set theory. So that's why it seems like we are introducing something new into our set theory that cannot be expressed in terms of whatever we have already got in set theory, namely all the operations, union, intersection, all the axioms of sets, etc. But fortunately, that is not the case. In fact, we can define an ordered pair using only whatever we have got in set theory so far. So this remark says that. Let us write some more things about it. This is because given two objects x and y, we have defined the ordered pair to be a new type of object let me quickly refill. That is, our assumption is that given x and y, an object of the form exists. It may seem like a stupid question to ask that if x and y are given, whether this ordered pair exists or not, but you have to understand that in this context, in the context of axiomatic set theory, existence is not merely existence. Existence means either you are introducing something new into the theory, or you are expressing that new thing in terms of the original axioms. That's what existence means. So if we are simply assuming that such a thing exists, then this is something new we are introducing to set theory. But the remark says that it will say now that that is not the case. Although we have introduced ordered pairs like some new objects that whose existence we are assuming, but actually ordered pairs can be defined only in terms of the set axioms that we have we have come across so far. So that is the next thing. However, ordered pairs can be defined in terms of the axioms of set theory in such a way that we need not postulate their existence separately, and this will be investigated in the first exercise. Usually at a lower level, when we are introduced to Cartesian products, ordered pairs are taken as some primitive object about which we already know, and that comes from the fact that at a very early stage in our mathematical development, we are introduced to graphs of functions. While drawing a graph, we are first asked to make a table of some values of the function at some points, then that table gives us some ordered pairs of x and y coordinates. So from there we gain some familiarity with ordered pairs, and then we are suddenly told that ordered pairs are not necessarily of just numbers, but you can have any object, and that's how the concept of Cartesian products is introduced. But from our point of view, since everything has to come from axiom or has to be introduced separately, so that's why these things are appearing. Whatever we will ultimately get is not something different from what we already know about Cartesian products, just the treatment is different and more logically more rigorous. And then after this there is one remark which is although not that important, but still since it's there I have to mention it. It's about use of parentheses, the round brackets. Terence Tao seems to make a big deal out of this, using parentheses again and again. We have used parentheses we have been using parentheses like this. Say, if you write 1 plus 3 times 5, you don't usually use parentheses because it has been assumed that multiplication takes precedence over addition. This one is calculated first and then with the result you add 1. This is convention. However, if you want to really mean that we have to add first and then multiply, then we use parentheses, because otherwise it becomes ambiguous. So that is one use. Another use is that we enclose arguments of functions inside parentheses. But now we are using ordered pairs also. We are writing ordered pairs and enclosing them within parentheses. So Tao's point is that we are asked to not get confused about these different usages, which is, I don't understand why this has to be said. It's clear from context, no? So he writes, we have again overloaded our use of parentheses. We not only use them for grouping of operators. Grouping of operators means those operations that you have seen just now. And grouping of operators and enclosing arguments. This is a function, this is the argument, we are enclosing it using parentheses, that thing. But we are also using them to enclose ordered pairs. This, however, does not cause any problem in practice, since one can usually understand what the symbols are intended for. From context, which is quite easy to understand. The thing is that you don't have to bother about how they are being used. From the context you will figure out what the matter is. Okay, now we come to the definition of Cartesian product. So far we have defined ordered pairs. So this is definition 4. Tau's numbering goes serially. Let x and y be any sets the Cartesian product of x and y denoted by x cross y is defined to be collection of all ordered pairs whose first components belong to x and whose second components belong to y. That is, x cross y is defined to be the set of all ordered pairs such that x belongs to x and y belongs to y. In other words, an object A belongs to the Cartesian product x cross y if and only if A is an ordered pair for some x belonging to x and y belonging to y. Okay. Now there is one problem with this definition. The problem is that, you see, how are we approaching set theory when we are following the axiomatic treatment? We are approaching set theory like we have to have some sort of reason or some sort of axiom for each set to exist. Merely saying that for given two sets x and y, the collection of ordered pairs that can be formed from them in this way, so that the first coordinates are coming from x and the second coordinates are coming from y, does not guarantee that this collection is a set. As of now, it's just a collection, but we have to be able to say that it's a set. How? Either we have to take this itself as an axiom that Cartesian product, all Cartesian products which can be formed are sets, or we have to prove that they are sets using the axioms that we have seen before this. Okay, one of these two things must be true. The second is less desirable. I mean, the fewer axioms we have in a theory, the stronger it gets. And that's where the next remark comes from. So this remark says, how can I phrase it? Shall I phrase it like what is given here? We can write it like this. We have simply assumed that whenever sets x and y are given to us, their Cartesian product x cross y is a set. Just like the assumption that we have made after defining ordered pairs, that any two given elements, for them they can form an ordered pair and such an object exists. Just like that, it seems like having this definition, we are assuming that if x and y are given to us as sets, then their Cartesian product exists, or in other words, it is a legitimate set in our set theory. This, however, need not be assumed. Like ordered pairs can be defined using only the set theoretic axioms, Cartesian products are also sets, and that can be justified using only whatever we have got before this. Okay, so this is, however, not a problem in practice, and the justification is the first exercise. Okay, so now having covered this basic definition of Cartesian product of two sets, and having discussed in brief what the problems are about existence of these objects in our set theory, let us now look at an example. So this is our simple example. This example will illustrate further points about this concept of Cartesian product. So we are going to take two sets So X consists of 1 and 2 and Y consists of 3, 4 and 5. Then we are going to calculate their Cartesian product in both the ways, that is X cross Y as well as Y cross X, and then see what the sets come out to be. In X cross Y, of course, we will have ordered pairs. The first coordinates can be either 1 or 2, the second coordinates can be either 3 or 4 or 5. So if the first coordinate is 1, the second coordinate can be either 3 or 4 or 5. Similarly, if the first coordinate is 2, the second coordinate can be either 3 or 4 or 5. So this is X cross Y, and like that we can calculate Y cross X. Now the first coordinates will come from Y and the second coordinates will come from X. 3, 1, 3, 2, 4, 1, 4, 2, 5, 1, 5, 2. Looking at these two sets, you can see that they are completely different. In fact, they are disjoint. They don't have any element common. Okay. Note that as sets X cross Y and Y cross X are different, in fact disjoint. They are as different as any two sets can be. There is nothing, no similarity, no common, I should not say no similarity, but no common elements at all. But still we feel that they are quite similar. For instance, they have the same number of elements. Six elements each one of them has. And this in fact will be proved in the next section, specifically in the fifth exercise of the next section. Okay, so Cartesian products can be formed in both the ways, and they are not necessarily the same set. In fact, most of the cases they are different. Now we come to a different thing altogether. Let f from x cross y to Z be a function where x, y and z are steps. So it's a function whose domain is a Cartesian product. We can view f as a function of one variable that maps an element this in the domain onto an element f of x comma y in Z. Okay, it's a function whose input is this ordered pair which is treated as a single object.